Okay, so I think everybody is ready for something a little lighter than some of this number theory. Shock. Okay. So I want to talk about extractors. I should write it here. And actually, Jean was pointing out that there is an extractor here that was meant to actually extract erasers that fell into the... but actually, we are going to talk about randomness extractors. And in fact, you'll see that as I talk about it, you'll see that both Jean and actually Peter too were talking about them, and Russell in some other way was using very similar concepts. So let me tell you the sort of motivation that gave rise to the type of questions we are asking. The motivation was the following. Randomness is basically used everywhere. People used it since the beginning of time for, gambling, and later statisticians, physicists. It's something we use all the time. And then within computer science, it's extremely important to cryptography. There are no secrets without randomness. And people use it, of course, in probabilistic algorithms. And so we need these random coin tosses, perfect coin tosses, which we assume everywhere in lots of these applications. And the question is where to get them from. So one thing is to say, well, it gets us to philosophy that Peter defined well. Is the world deterministic or inherently has some randomness in it, maybe from quantum mechanics or something like this? We are not going to argue about this here. We are going to postulate that there is some randomness in the world. And the question is, what kind of randomness can be useful to generate truly random bits? And you can just look around you and you see lots of unpredictable phenomena of all sorts. And the weather, or the stock market, or the length of time Jean will talk when he's given 45 minutes. And so you can sample any physical phenomena and just get a sequence of bits, and they would typically be correlated and dependent as opposed to independent. And then you want to take these bits or these samples and create from them a good random coin. We actually want many random coins, many independent random coins, but today I'm going to simplify everything and talk about just generating one random bit, or as close to a random bit as we can get. So we just start by defining a mathematical model for this problem, and it's very simple. We have some universe, some domain D in which we live. That's a finite domain. And on this finite space, we have various probability distributions that sort of captures the fact that we don't really understand the phenomena we are sampling from, but maybe we have some idea about it. Maybe we know some entropy about it, that it has some amount of entropy. Maybe we know that it has some structure. So there are distributions, x prime, and so on there. So we have S, which is a family of probability distributions on D. So you have some unknown distribution, maybe chosen by an adversary. That's the distribution we are sampling from. And what we would like to do is to take this sample, this random sample, and from one of these distributions, and make a good coin out of it. So formally, what we are looking for is a function. This will be the function that will give us our bit. We want a bit, it's plus minus 1 or 0, 1 or red and blue, whatever you want to call it. I'll mostly use plus and minus 1. So we want such a function. And now when is this function good for the family of distributions the family of distribution S? Well, take any one of these distributions, and for each of them we want the following. We just look at what is the expected value of f. How, if, look at the expectation of f of x. If this is with probability half 1, probability half minus 1, then we get expectation 0, and that's a perfect coin. Okay? And we say it's a pretty good coin. It's epsilon biased if this is at most epsilon. We'll call this epsilon biased, which really means epsilon unbiased, or biased by at most epsilon from a truly random coin. And what do we want? We want that for every distribution in our family, this will be true. If for every possible distribution that we are considering,
that doesn't depend on the size of the set.
What? Epsilon may depend. Often you'll want it to depend. Often you'll want it to be, going to 0 with parameters. But S, this family of distribution. And in this case, if you have such a function, then you have a way of generating randomness, and then we call f, and if this holds, we call it an S epsilon extractor. And the question is, the general question is, for which families of distributions can we do that?
Sorry,
okay. F of x? So think of x is a distribution. X is a random variable. So you evaluate f on this random variable, you get a distribution on +1 and -1, and you see how biased it is. If it's half-half, you get a perfect coin.
Okay. You say we can do that efficiently?
Yes, very good. So it's very good. In lots of the problems I'll talk about, I'll just give a series of examples of such families of distributions, and some things we know and some things we don't know about them. And like Van said, it's really, really, really important that if we are ever going to use it in algorithms or in life, we want f to be efficiently computable. It will be interesting to also consider, at least for understanding what to expect, f's which are not random f's, but we will be interested, that a solution is good only if it satisfies this. So we are looking for efficiently computable extractors. Okay, so let me start giving you examples. Questions about the definition. So let me just say in terms of a picture here, f is supposed to be, given that this is a family of distribution, f should somehow divide the space into its -1 part, and so this is f equal -1, and here f is equal +1. It somehow should divide the space that no matter which of these distributions you take, it's about half on the half on one side and about half on the other side. So it's like this is why it's related to things like discrepancy theory, for those of you who are into this field. It's related to it's a good way also to view results in ergodic theory and statements. Well, you'll see in exponential sums, we'll get to this. So let me give you first a very simple example. The simple example is, suppose I already give you, the kind of distribution I give you is already a distribution on biased coins, but you want to improve their quality. So suppose, so we start defining these families of distribution. So the first family will be, I'll call it B delta. So it's a family of distribution. So let me first say that what is D. I'll have to say what the universe is each time. It's just all binary strings of length n, and that will always often be the situation. And B delta is these distributions, which so it's a distribution that is just a sequence of bit xn, such that the xi's are iid, so are independent and identically distributed, and each of them is a biased coin, but and each xi is is delta biased. In other words, somebody, let's say that delta here is number strictly less than 1. Let's say it's 0.99. So somebody is tossing coins with some probability that it's at most between 0.01 and 0.99. He's not telling you what is the bias. He's tossing the same coin independently n times. It's giving to you the sequence, and you are supposed to generate from this sequence one bit that is, looks like random, or very close to random. What would you do?
So in this case, S had only one.
No, because a delta bias just means it's more, so it's some bias between, 0.1 and 0.9 or something, but you don't know it, right? So that's a famous problem that von Neumann encountered, and anybody wants to? What?
Adam.
No, Adam is not such a good idea. Here's von Neumann's solution. The idea is the following. So even if you don't know the bias, but just consider x1, x2, x1 and x2. Well, if they are, so suppose the bias, the probability that each of them is 1 is p. If they are different, then both 0, 1 and 1, 0 have the same probability, which is p times 1 minus p, right? So if they are different, take the first one as your answer, and it's an unbiased bit, completely unbiased, right? And so look at the first pair. If they are, different, take the first one. If they are the same, move to the next pair, x3, x4. If they are different, give the first one, and so on. I'm not going to write down this procedure, and you go up to the end. If you are really unlucky and all the, in all cases they are equal, well, you give up and say 1, right? So what?
So if you would have taken the sum of the two, it's the first idea, because still this is.
Sorry, that's right. It's bias. Sorry, I take it back. It's a very good idea to take the sum. Take the sum modulo 2. I take it back. That's a different solution. It's very good to. So in both solutions, I was thinking already about the next model, but sorry. So in both solutions, what you get is that, I implicitly define for you a very efficient procedure, or two efficient procedures, what Lenny suggested and what von Neumann suggested, that gives you an f, which is b delta for any delta, which is less than 1, and epsilon extractor for epsilon, which is exponentially small, some c delta. So you improve fantastically the quality of the bit. Okay. Now let's look at a very similar situation where still we have binary strings, but we look at a superclass of these distributions. Let's call it b delta prime, which will have basically the same amount of entropy in the distribution. So every coin will be delta biased. Okay, but now they are not independent. They are not necessarily independent. What you are told is that, well, it's all distributions which are drawn on n bits. And what you are told is that, let's say they are tossed in sequence. The adversary tosses them in sequence. And at every step, he's looking at the history and then decides what bias to put on the coin. Okay? So all you know is that xi, so for every I and for every previous bits that were tossed, xi conditioned on x1 equals sigma 1, xi minus 1 equals sigma I minus 1. This bit is still delta biased. Is not completely 0, is not completely 1. So you get positive entropy with every bit, but maybe in a way that depends on the previous history. So how would you extract, how would you improve the quality of this? Nobody has an idea. That's good, because there's a beautiful theorem that I really suggest whoever haven't seen it to try to prove it themselves, is that for every function, this is impossible. This task is impossible. So for every function, there exists x in this. There exists a distribution like this, which such that f of x is not delta prime. Well, it's not epsilon biased for any epsilon smaller than delta. You can ask for as many bits as you like, and the entropy is growing and growing, and still you cannot do better than take the first bit, which is pretty lousy. Okay, so that's a situation where you can do nothing, explicit or non-explicit. And we will get back to these kind of questions later, what to do in situations where you don't have such extractors. Questions so far? Everything's... What is? Sorry, yeah, Santa and Vazirani. Santa and Umesh, Miklos Santa and Umesh Vazirani, that's from the mid-80s. And in fact, this paper more or less started the theory of extractors within computational complexity. Okay, so let me move to structures, to families of distributions that where the structure is different than what was given here. So first I'm going to talk for about 15-20 minutes about algebraic structure, and then we'll move to more combinatorial structure, and then we'll be done. So we are still in the Boolean case, but let me put the algebraic structure. I think of the Boolean cube now as a vector space f2 to the n. Okay, and the sources, which I'll call L2k, 2 for f2, L2k will be just all the distributions which are uniform on k-dimensional subspaces. Okay, so we have f2 to the n. Inside it, there are lots and lots of possible k-dimensional subspaces. K is a parameter. And we have the uniform distribution on one of them, and we want to extract randomness from that. So pictorially, we have the... I don't know why Peter can draw only in 2 dimensions. Here's the 3-dimensional. This is f2 to the n. And inside it... Yeah, that I agree. Yeah, non-abelian I cannot draw. Inside it, you have maybe a 2-dimensional subspace. Well, you have many of them. So what we are trying to do is color. So our function f will color, will color the points of this Boolean cube by +1 and -1s. And we want it to be colored in such a way that whenever we look at a k-dimensional subspace, roughly we have the same number of +1s and -1s, right? So when we average, we get a good coin. Okay, so what can be done? So let me tell you one easy theorem. It's sort of an observation, which you are again welcome to prove, is the following. Assume that k is quite large. So k is greater than half plus alpha n. So you have more than half the dimension. Okay? In this case, if you take f to be x1, x2 plus x3, x4, xn minus 1, xn, let's say n is even, and this is arithmetic modulo 2, okay? You take this simple quadratic polynomial, then I claim that this f is a L2k for this k, epsilon extractor with epsilon exponential again. And that's an exercise, a little Fourier analysis. So if the dimension is really high, then you can do it. But how now we get to the point of comparing explicit to non-explicit constructions, we ask ourselves, well, how good is this result? Is this the best that we can hope for? Or maybe we can do it even for much smaller subspaces. And the answer is that you can do better for much, much smaller dimensions if you are willing to, to tolerate non-explicit construction. So just in terms of our goal, where should we set our goal? We should set it according to the following, again, well, according to the following fact that most f, so a random f with probability 1 minus little 1, most f are actually L2k epsilon extractors, even if k is about, greater than something like 2 log n. Much, much more for really tiny dimensional subspaces. You can have such a coloring that will be good for all of them. And epsilon will be as good as you want, you can hope for. It will be exponential. Okay. So what does it mean? It means that we should, this is a very explicit function, but it, all you can guarantee is that it does well on really, when the entropy is really huge, it's more than half. And yeah? What? Smaller is false. Yeah, this is the best. If it's smaller than half log n, for example, it's false. Yeah.
No. In the quadratic form.
In the quadratic form, it's false for 1/2. Yes. Yes. Yeah. If you pick half, that's a very good point. So if you take all the even coordinates to be 0, it's a n over 2-dimensional subspace, and the function is constantly.
Has a degree into play.
Okay, so well, you can try lots of things. Let me state one result, the best result known. So we are aiming for, we are stuck just above 1/2, and we are aiming for logarithmic, and like Peter,
I have to put his name there.
Yes. So it turns out I'm not going to go into methods here. I'll just state theorems and problems. So Jean has a polynomial. So f will be a polynomial with constant degree. And it will have the property that it will be a L2k epsilon extractor for k, which is, let's say, beta n for every positive beta. It actually goes a little bit smaller, but let's just state it like this. Okay? So you can handle linear dimensional subspaces. So much better than 1/2, but much farther than.
Is the degree related to beta?
Yeah, and the degree is related to beta. Yeah, that's right.
Is this explicit?
Yes, completely explicit. And it uses arithmetic combinatorics, and it's quite complicated. I'll state another theorem with Jan that later that's much simpler. But this one is, it's quite complicated. And the open question I want to ask here is the obvious one. I mean, bridge this exponential gap between linear and logarithmic. So I don't want to talk questions about this. I don't want to talk much more about the algebraic setting. I just want to tell you that there are lots more works on it, and I want to.
Actually, there is a natural candidate which is the multiplicative character.
Yes, I guess the multiplicative, right. So you could just look at the sequences sitting in some prime field, the binary sequences encoding an element in some big prime field, and take for example, the quadratic.
It's a short exponential sum of characters.
It's the multiplicative character on the subspace.
Which the methods don't have. No.
Yeah, 1/2 is not known for this particular example. So let me tell you about somewhat. I do want to talk more about the linear, the algebraic structure, but in a different setting. Here is one situation which makes the game simpler, and this is in work of Raz and Gabizon and Raz. And even though it makes things simpler, and I actually want to show it to you because I want to connect it with this extractor game to exponential sums, there are other, well, okay, I'll talk about it later. So what did they look at? Well, they simply said, well, let's look at large fields. Suppose we look at fp to the n, where p is allowed to depend on n, it can grow with n, okay? When you ask the same question, well, let's denote pk to be just k-dimensional subspaces like before. So uniform distributions on k-dimensional subspaces. What can you say in this situation? And their theorem, and I want that will be the only proof I give, is the following, that there is an explicit extractor. So I'll tell you the explicit extractor a little later. There's an explicit function. So again, the function is from fp to the n to plus minus 1, which is an LPK epsilon extractor. So for what k can we do it? So we'll pick p to be sufficiently large. So let's say n to the 4th. Okay, so p depends on n. As I said, it simplifies the matter, and you'll see why. So we take p large, and this will allow us to get an explicit extractor for subspaces of dimension k, actually for any k greater than 1, even for lines. And epsilon here will be, let's say, 1 over n. Okay, so you see, you asked before, Peter, there in many cases epsilon is... yeah. Okay, so why is it simple? So it's simple because Jean didn't state the Weil theorem, even though he stated many other exponential sum results. So let me state the Weil theorem, and then we'll see why this is a consequence of just the Weil bound. Okay? So, well, you have to do something, but it's simple. So let's look at the Weil theorem. So let chi be the quadratic character on fp. So just whether a number is quadratic residue or not, plus minus 1. And suppose that you have g, a polynomial, which is not a constant, or not a square, and the degree of g is at most d. So we have a bound on the degree, and it's not trivially false what I'm going to say. Then what you have is the following. The sum over all z in fp, the quadratic character of f of, g of z. Okay, that's the exponential sum, multiplicative character. It's at most d square root of p. That's the famous Weil bound. I'm sure people have seen it. So let me just first explain why Weil was working on extractors, and then we'll see. Well, what is the... This is... that says that a certain coin here is very unbiased, right? The coin chi, evaluated on a family of distributions. So for him, he was looking at the following family of distributions. Let's call it PD, which is the random variable is simply g of z, where z is random. G is uniformly random in fp. So the type of questions, Zev, you want me to answer? No. So what distributions are we looking at? For every polynomial of degree at most d, which is not constant, not a square, we have the following random variable. We take a random field element and evaluate g. That's a distribution. And what is Weil telling us? That the sum is small, where if I replace sum by expectation like we had before, then I'll get the root p over here. right? So it tells us that you know, this bit is unbiased. So for this family of distributions, chi is a PD and d over root p extractor. So this is probably the earliest result in extractor theory. And now we want to use it. Well, this is about univariate polynomials. There we have subspaces. How can we translate this Weil theorem into the language of subspaces? And Gabizon and Raz have a very simple solution, which is the following. You get this sequence x1 through xn, which is just elements in fp, so x1. So I want to define f. So what is f on x1, xn, well, these are just field elements, right? This is what we get from that comes from some linear subspace of dimension, maybe 1, maybe it's a line, okay? So, well, that's very simple. Let's take x1 and then x2 cubed and x3. We just take successive odd powers. Why odd? Because we don't want to fall into squares, right? So we take this polynomial, and this is a good function. This is an extractor. The claim is that this is an extractor for every line and every higher dimensional subspace. Why? Sorry, chi. Thank you. Quadratic character. That's our function. Chi of this. Why is this true? Because let's look what happens when you evaluate it on a line. So what is a line? So if this is a line, then there are linear functions, L1 or affine if you want, Ln, affine functions from fp to itself, such that this is simply L1 of z up to Ln of z for all, so for a line, for all z in the field, right? And now, when you take these linear functions and substitute them here, you would get a polynomial of odd, there is no cancellation because there are different degrees. So you get a polynomial of degree 2n. Yeah, the degree remains about n. So here we have about n. Here we have square root of p. And you can see why I took p to be n to the fourth. When you divide them, you get 1 over n. Okay, so it's a very simple translation to this exponential sum. Let me.
We compute chi?
Yes, very easily, because a prime this size, we have no problem. But in fact, chi you can compute for primes easily, because let me say that chi of z, simply z to the p minus 1 over 2, which you can compute by. Yeah, so it's really easy. It's a very efficient function. I don't want to write much more about the algebraic setting, but I want to tell you about directions in which this developed in the algebraic setting, which is here the random variable is defined by some linear maps, right? And you can ask yourself, what happens if instead of linear maps I have polynomial maps? Well, in the case of linear functions, you can, a linear subspace is both the image of a linear map and the kernel of a linear map. When you move to higher degree polynomials, these are separate questions. You can look at the image of a polynomial map on a random input. You can look at a uniform distribution on the kernel of a polynomial map, which is an algebraic variety. And you can ask yourself, can one extract from such distributions? And the answer is that there are lots of things to, there are lots of more things to do there. There are some results, some we have with Zeev and Ariel Gabizon, and some recent ones that Zeev Dvir here has for algebraic varieties. And they work, the main disadvantage is that they work only for fields, prime fields, which are exponential in the degree.
Are you using fancier bounds?
Very good. Yes. So so after Weil started, lots of other number theory, lots of other mathematicians started doing extractors, and in particular, Zeev is using Delin for some part of his work, and actually something that is quite more useful for some of the results is Bombieri's theorem, which talks about exponential sums, not over a field, but over a curve. And that other really nice things in algebraic geometry are used. So let me tell you about the last thing I probably have time to tell you. Oh, when did I start? 3:40, okay. Well, I have 10 minutes. So the last model I want to talk about is a much less structured model. And here the distributions so you can think of the domain as a big matrix. Here you have all strings of length n. So this is what you are supposed to color. You are supposed to give plus minus 1 values to this entry. And the kind of distributions that you are looking at, what's called independent distributions, they are just subrectangles. You look at A1 here, A2 here, two arbitrary subsets that are not too small. And what you want, so you're putting plus 1 and minus 1 all over, and you want that they will be roughly uniformly distributed, half-half, on every such large rectangle. So I2, again, 2 is for this because there are 2 here, and K, independent with entropy K, are all the x's which are uniform, all the distributions which are uniformly distributed on such A1 times A2, with this AI have size at least 2 to the K. So have entropy K each. Okay? Okay, so again, so let me say more quickly the story similar to what I told you in the case of, it's amazing how similar the story is to what I told you in the case of the F2 to the n. First of all, what kind of pseudo-random matrix you can take here? Well, I will not ask because I'll tell you the answer. The Hadamard matrix. What's the Hadamard matrix? Just so we have x's on the rows and y's in the columns. Then it's just just this inner product, same polynomial we saw before. That looks like a pseudo-random matrix, and in fact, H is just like before, I, 2, and here the K will be half plus alpha n. So again, if the entropy, like before, is bigger, sufficiently bigger than half, then you get an extractor with exponentially small error. Alpha n. So if, again, this is somehow a trivial case, this is just Cauchy-Schwarz. In fact, the same Cauchy-Schwarz, the way Jean expressed it. So that's an exercise. And again, you can ask yourself, well, how close it is to what we can hope to do. And you do a random function on this. So you take a random function from 0, 1 to the n squared to plus minus 1. And you ask, how good is this? Well, it turns out that this will be almost surely is a much better, maybe 2 log n extractor. So again, you can extract, at least non-explicitly, from sets of much smaller size. The entropy is logarithmic, so just the size is polynomial inside this exponential space. And you can ask yourself, well, again, what can we do better than this trivial slightly over 1/2? And like in the story before, there is a theorem of Bourgain, which is somewhat weaker than before. And he defines quite a simple polynomial. I will not define it, but I'll just tell you that it's an explicit extractor for I2k extractor for k, well, we would have loved to have a result like before for any linear entropy even, but even this we don't know. Even 1/3 we don't know. But we know 0.4999, and I think, yeah. I don't think you try to improve it like removing the logs, removing the, yeah. But anyway, in some sense, there's no method of iterating that construction, and that has to do with the, whether arithmetic arithmetic combinatorial machinery, it's asymmetry with respect to addition and to multiplication. So there are a host of things you'll get into if you try to improve this. And
the Weil thing would allow you one of them to make much smaller.
yes, and that's absolutely true. In fact, if you can use Weil theorem and handle an asymmetry case where k is bigger than 1/2 the entropy in one dimension and only logarithmic in the other. That's pretty simple, but decreasing them both to 1/3, and we don't know. So let me say just one thing that we can do when we don't know this, and we want to simplify our problem, and in fact we simplify our problem to an area that existed long before extractors, and this is Ramsey theory. And some people, I'm sure, noticed that this picture is probably reminds them of Ramsey graphs. So let me just make these connections explicit and state the results for Ramsey graphs. So what is a weaker demand from this explicit function you are taking? Well, one thing you can say, well, you want it to be unbiased, half zeros, half ones. But the weakest requirement, which is non-trivial, that you can make is you just don't want all of them to be the same. You don't want your output bits to be constant. So f is a disperser if for every distribution, for example here, f of x is, +1 and -1. So on every distribution, you at least sometime output 1, sometimes output -1. Maybe it's not unbalanced, but at least you do this. So in other words, f is not monochromatic on any and here the distribution doesn't make any, it's not important, but only the support of the
Density version.
It's not a density version. It's okay. Yeah, you can call it, although I would call it a Ramsey version. Just it's whether you have a monochromatic set.
But it's a density product.
You still, yeah, so we are asking for a disperser instead of an extractor, let's say for this family, the family of rectangles inside this big matrix. And there is a graph interpretation. You can think of this matrix as just describing a graph, and you want that subgraphs will not be monochromatic in the sense will not have, if these are just a coloring by red and blue the edges of the complete bipartite graph, you don't want a small subgraph in which all edges are blue or all edges are red. I'm not making the connection formal, but well, you can think about it. It's very simple. But you can ask the same question for which you can ask for an I2k, and now epsilon doesn't appear here. There is no error. You just want it to be not monochromatic. So for what k's, for what values of k, for what size of rectangle can you make it not monochromatic? And the first result was in a paper with Boaz Barak, Kindler, Shaltiel, Sudakov, in which we handled the case that k was, well, any linear, any constant fraction of n, and we can get a disperser, an explicit disperser for such rectangles. So we don't guarantee that it's unbiased, but we guarantee that at least you see both zeros and ones. And then in a paper with, again, Barak, Rao, Shaltiel. We got k to be n to the little one. So any n to the epsilon, in fact, quite smaller than that.
So you get each value with positive probability, right? It's not just...
In fact, we get every value with positive. Yeah, we get every value with positive probability. It's explicit. So it gives Ramsey graphs with these parameters. Of course, the best parameters, even for extractors, are logarithmic, so there is still quite a gap to go. There's another gap here of a completely different nature, whereas Bourgain's extractor is an explicit simple polynomial function. This is explicit, but it's quite a complex function. It's not it's very easily computable, but its description is much uglier, let alone the proof that it works, which is much, much uglier. So these are two places in which we can simplify this. I kept putting 2 here for 2 independent distributions. You can ask this question about, higher, 3 and 4 and 5 independent sources. That's exactly what Jean was talking about when he talked about the multilinear extension of Cauchy-Schwarz and talking about it as an extractor. It is an extractor exactly for the situation where you have many independent copies. 2 is the hardest case, but in order to solve this problem, you need to appeal to results about extractors in higher dimensional spaces and to use arithmetic combinatorics. And yeah, so that's what you do there.
But for 3 extractors, you have the full thing.
No,
For 3 sources?
no. Although it's a situation much better than 2, no, we don't have. Yeah. Right. So, okay, I think that I was going to say more, but let me just say, close with a sentence about what I didn't talk about. I showed you in the beginning an example for which there was no extractor, right? So some families of distributions are just too rich to have one extractor. So there are some sources S for which there is no extractor. In this case, what you do is you do the next best thing, which is take a family of functions, most of which will be good extractors for your source. So you have some functions f1, f2, fl, such that for every distribution in the source, all but epsilon L of these fi's satisfy the expectation of fi x. And the problem of making L small, which is really important if you want, again, an efficient algorithm. So in fact, what you can achieve existentially and what today we can achieve completely explicitly is something polynomial. So L is polynomial in n over epsilon. And that's up to polynomial the best you can hope. But in fact, the optimal, which would really be interesting to get, that's another really interesting open question, will be n over epsilon squared.
You're talking about which distributions now, right?
Very good. Very, very good. So for example, the distribution I defined before. But in fact, it's more than this. It's just the one-dimensional. So since we had 2 dimensions and many more dimensions, let's just go to 1 dimension. We have d is 0, 1 to the n, and S is simply all distributions uniform on some set A of size at least 2 to the k, and this should work for any k basically, any k greater than log n. So if you have enough entropy, just a little bit of entropy, just logarithmic entropy, then you can achieve this weaker notion of extraction, namely a set of functions, most of which are good for any source. And it turns out that these objects are much more useful and interesting and applicable, then all the objects I talked about before, really applicable in error correcting codes and in data structures, in algorithms, and in cryptography. But that's a topic for another lecture, so I'll stop here. Questions?
Since you put phase bound on the board, and since John started out at 100 miles an hour, you might just say that one of his things that he was explaining was to give bounds for exponential sums, not where that's a character multiplicative, but additive, where the interesting thing is that b is fixed and d is large, and that bound is useless where all this arithmetic I mean, I'm just, since he went so fast, and he went to the trouble of writing the bound.
Yes, in fact, I should say that this kind of bound is known, first of all, for other multiplicative characters. It's known for additive characters, and its version for additive characters is often much more interesting for applications to extractors because they give you the ability not only to extract one bit of output, but many bits of outputs, really getting all the entropy embedded in a source out in a uniform distribution. So, but again, a separate story. More comments? Well, we are, Jean was supposed to say in the beginning that we are waiting for your solutions of all the open problems so we can write them in our grant. And thank you.